great pleasure, therefore, for me to call on Dr. Burke to address us on the matter of chaos to order lasers and VLBI.
Didn't get back to MIT until '65. I think it's a marvelous chance here to go over two different kinds of history. Grote Reber, who first realized the importance that angular resolution would play, and then the events. And then a review of the events that led to an approximately 8-fold increase in order of magnitude of angular resolution. At the same time, there's been about an 8-fold increase in the number of authors on a typical paper. And so we can conclude, therefore, that the number of authors is proportional to the logarithm of the angular resolution. The other point that I wanted to start off with is a disclaimer. That is, I'm not claiming to be first in anything. And I have documentary proof. Here we have a letter. Boy, it's pretty hard to read. Well, that's all right. This is a letter dated February 15th, 1967. It's a memo to Paul Sebring, Dave Hesching, from me. Subject, OH interferometry. Boy, this is, let me see this. OH interferometry between NRAO and haystack millstone. And the first paragraph says, during the past few weeks, a number of conversations have been held between J.M. Moran, M.L. Meeks, R.P. Ingalls, K.I. Kellerman, and myself concerning the feasibility of a synchronous interferometer measurement of the stronger OH emission regions using the 140-foot NRAO telescope and either the haystack or millstone telescope of Lincoln Lab. Informally, Jodrell Bank has reported observable fringes with a baseline of 1.9 times 10 to the something wavelengths. So the next step to a baseline of 5 times 10 to the 6 wavelengths should be a reasonable extension. The use of separated but nearly synchronous local oscillators, as in the VLB experiments between NRAO and Arecibo, is a natural observation method and has the additional advantage of proving the system with relatively loose restrictions on timing and oscillator synchronization. Comment at the top. Paul Sebring received this February 16th, sent it on to Mel Stone, who received it February 20th. It says, Mel, this looks easy. I'm concerned over any diversion of Ingalls, however. Have you looked into this? And at the bottom, there's a note saying, can be done, easy on 3300, the computer they had. So the motivation then came late, much later than the hard spade work that had been done by the other two groups. But I thought I would go through the motivation, and you can see why I think we still made a contribution, even though it was not the contribution of being first. When I came to MIT, the OH molecule had taken on a special burst of excitement because although the radio lines were discovered between MIT and Lincoln Lab with complementary roles being played by Al Barrett and Sandy Weinreb, after seeing the lines in absorption, then in 1965, Harold Weaver's group at Berkeley discovered that there were OH emission lines, which had such peculiar properties. They were intense, narrow, multiple, that for a while they had been nicknamed Mysterium. Well, of course, they turned out to be Ordinarium. And just within weeks of the time that I arrived at MIT, Al Barrett and his colleagues at Lincoln Lab had established the fact that the that the lines exhibited very, very strong polarization. So there's something very strange about them. And I had come from a background of interferometry, and I could see that right next door to the Haystack radio telescope was the Millstone radar, which was a perfectly good radio telescope. And so I proposed that we should use them as an interferometric combination. Fortunately, we had some very talented people working with us. Alan Rogers probably deserving special mention in this effort. And just to remind us, I'll show one slide, the first slide of the complex, where one can see the Haystack antenna here and the old Millstone 85-foot antenna in the foreground, located on a tall tower. And it turned out that tall tower plays an interesting role in the history. So a cable was laid, a set of cables were laid between the two antennas, and Alan Rogers built a phase stabilization system so we could have stable local oscillators. And indeed, we obtained fringes with about 1 arc-minute resolution on the OH lines. This was done, we started work in late '65, and the fringes were obtained in June of '66. But of course, that's just interferometric fringes and not VLBI fringes. There was no evidence that any of the OH sources were being resolved. And the brightness temperatures already were getting up so high that clearly we could say that there was no evidence for expecting any particular angular size, so we should press on. The Harvard group, who had been our competitors in the molecular game, had a 60-foot antenna at the Agassiz station, only 10 miles away. And it turned out that on the Agassiz property there was a fire tower. That fire tower could be seen if you stood on the upper reaches of the Millstone tower. And that established mutual visibility. It meant we could do a cheap experiment rather than an expensive experiment that would have required the building of towers and such like. So we decided we would use the Millstone antenna and Harvard's Agassiz station 10 miles away in an interferometer experiment that would have a resolution of an angular resolution of about 3 arc seconds. The experiment worked, and there were some amusing experiences along the way. Lincoln Laboratory didn't quite know how to treat us, and I must say it was an interesting problem, because I would say that the management at Lincoln Lab back at Hanscom Field regarded us with something between fear and loathing. And on the other hand, Paul Sebring, the site director, was a marvelously protective site director and very successful in performing the juggling act of satisfying these rapacious scientists that he had to meet every day, and at the same time satisfying the bureaucrats back at Hanscom Field. Not all the bureaucrats were hostile, by the way, and of course that does help. I'll show a slide of some initial results, and this shows the upper slide is the relative phase between two of the OH lines, and you can see that the phase is shifting as a function of our angle. And of course, this meant that the two spots were not in the same position, and we derived what we believed was the first map of an OH complex showing the locations of the maser spots relative to the spot that we chose as a reference feature. Now, at this stage, with upper limits of 3 arc seconds and no signs of angular resolution, it was absolutely clear that the longer baselines, much longer baselines, were needed. These fringes were obtained in November. The Millstone Agassiz fringes were obtained in November of '66. And so I visited Green Bank often enough to be quite aware of the VLBI work that Ken Kellerman had described. And in the winter, became quite aware that their experiment between Puerto Rico and Greenbank was not working. Now, here we were wanting higher angular resolution, knowing that there were problems, and as usual, you're self-confident. You say, well, we know how to do it, and those guys don't know how to do it. But I think actually we did have a reasonable motivation. Namely, we knew that the experiment would be simple. And the reason we knew it would be simple is because the lines were very narrow. If the lines are narrow, the coherence length is long, and therefore the tolerances on timing would be clearly less stringent. And so we did have a very good physical motivation that was almost eleemosynary. That is, we knew that this was one way to go if the other experiments continued to have problems. Of course, there was an edge of competition, I'm sure. We would have loved to have been first, and I think that for the NRAO group in particular, it probably provided a useful spur to them to get on the ball and get things working. So we like to think that at least we were helping in a certain sense, and certainly we derived great advantages from working with the NRAO because they held up their end very effectively indeed. And it's for that reason that I was sniffing when people were saying, well, maybe it would have been a long time if we hadn't had these technical things around. Well, I think that the OH masers are strong enough so that rather primitive equipment that was available a decade earlier, crystal oscillators, would have been quite good enough. And so we came in, therefore, to VLBI with an entirely different set of motivations from those who were working on quasars. As Ken has summarized, even the quasar motivations were varied. The work on Jupiter at Florida State, at the University of Florida, had a completely different set of motivations. They considered the experiment to be so trivial, and in their case, quite correctly, they considered that the results really weren't that interesting. That they performed the experiment before the long baseline experiments were performed in the rest of the world, that is in February of 1967, but they left their data in the can for over a year before reducing it. So, but I don't think one can fault them. It was an easy experiment for them to do. They could use audio recorders, and knowing that they already knew that the bursts came from small regions, and knowing that they came from small regions meant that they didn't feel they needed extra information. Nevertheless, they could have been claiming they really were first. Well, events moved very rapidly. One reason that we were confident that the VLB experiment had to work was that we did a beacon experiment in the course of the Millstone Agassiz experiments. On the fire tower at Agassiz, we mounted a target transmitter. Both radio telescopes were aimed at that target transmitter, and when the local oscillators were offset, we could see the false fringe rate due to the offset local oscillators. Then when the two local oscillators were locked, then just the instability of the radio link determined the way things behaved. In the course of this experiment, Jim Moran and Alan Rogers opened up the link, the phase control link from Haystack, from the Millstone antenna to Agassiz. It was very easy. They just unplugged it. And there was a free-running local oscillator at Millstone and a free-running local oscillator at Agassiz. They were both at Millstone. It was not really free-running. It was locked to the station standard, but it was just a very good crystal oscillator operating at the Agassiz station. And they could still see the coherence. And then later on, when they were actually observing a source, they tried the same experiment, and they indeed did see that they still got enough coherence to see the fringes in real time. It wasn't truly a VLB experiment, but it was performed in November of 1966, and it did show that we were quite confident that things had to work. Now, the actual VLB experiments on the OH line were carried out during the period of 8th to the 12th of June in 1967, a little bit after the continuing experiments, as we have heard. But it was no sweat, or almost no sweat. We were able to set up a simple spectrometer at each radio telescope, observe to see that we had a good strong OH line right where it should be in frequency so that no one had misset local oscillators. The signals could be seen and they were strong, and therefore we could record those signals. We could have recorded them on our audio recorders and still gotten an experiment. The first observations around the 8th and the 9th were immediately taken to the Green Bank data was taken to Haystack, and Jim Moran was there processing the data. He had had the major overall responsibility for the programs, although others had specific parts of the programs that they developed, and he could not find fringes. And somebody, we're not quite sure who it was, said, well, perhaps what we should do is to observe the OH sources when they cross that point where the hour angles of the interferometer baseline and the source were the same, where the fringe rate goes to 0. And so we changed the observing program so that we would get that magic moment. And I happened to be at Green Bank at the time. I took the new set of tapes up with me to Haystack. Jim Moran at that moment was alone in the computer room. I brought the tapes in. He hung the new tapes on the recorders, and then I went off to one side while he worked. I knew I couldn't help him. And then Jim, with a big smile on his face, came over and said, would you like to see what OH fringes look like? And there they are, cross power spectrum. And this shows 3 spectra with different frequency offsets, and here, of course, is the correct frequency offset. It turned out that Jim Moran's program, fringe offset, put into the program in the wrong sense. And so very shortly, he was able to go fiddle the program, get the correct sign of fringe rotation, and from there on, there were no problems at all. Of course, you can see the influence of the computer. That is the analog records here that show real fringes. You can see those real fringes. You can't see the fringes anymore. There's the fringe phase, there's the fringe amplitude. Fringe is just a complex number. And it was amusing that recently I sat on the oral exam of one of my students, and one of the other examiners, a rather older-fashioned physicist, said, well, tell me, how in these interferometers like the VLA do you observe the fringes? And so he began talking about complex numbers and visibilities, and it wasn't satisfying the old gentleman at all. Yeah, but what are the fringes? And they were just like this. That is, I was squirming, of course. I wasn't going to give my student the answer. But on the other hand, I knew that he knew what fringes were, but he knew of fringes in a very abstract sense, which is just a sign of the passing of the times. Well, so we got a successful experiment. Things happened very rapidly after that. We found that the water vapor lines that had been discovered by Charlie Towns's urging at Berkeley had properties similar to those of the OH lines. And of course, here's W3OH with the OH and H2O masers superimposed. A lot of astrophysics there, but that's beyond the scope of this talk. Things moved very rapidly then in the whole game. We went to transcontinental VLBI fringes and then intercontinental fringes by the end of '67. That is, I spent New Year's Eve at Hat Creek with Dave Cuddeback, and the Mark I recorder had stopped operating. And you can understand the Ampex repairman was not eager on New Year's Eve to come out to fix the recorder since he was in San Francisco and we were 300 miles to the north. So over the telephone, he stepped us through the system, and we discovered that there was a circuit that we could bypass and perform the experiment. So in those days, you really had to get involved in quite a personal way to get things working. We then switched our attentions to the H2O line, and we, in fact, did get successful experiments at the water vapor frequency. And I've got the titles of these things, and it's just fun to see how rapidly things did change. That is, at the very top is the August 66 letter we sent to PhysRev Letters. Then the developments of longer baselines, and right in here, they're a little out of order. There's the haystack millstone experiment. Then the VLB experiment from August 11th, 1967 Science. And the pace continued, and when you look back at this, you can see that surely things were right and the experimenters were enthusiastic, as we could see from the other schedules that were shown. Here were the first waterline experiment, which was done in December of 1969. So by December 1969, we were doing 1.3 centimeter VLBI. And then finally, of course, we were able to extend the baseline still further by going to the Soviet Union. Ken Kellerman's group were first. We went there second, but also had a good time because for a while we could hold the record of the longest baseline in the world. There's the paper there. You can see the Nablugenia Istochnikov Mazirnova Radio Isluchenia s uglovым разрежением, 0002 arc seconds. That's the part that matters. And so it was a very exciting time. And as you can see, I'm firmly convinced if we didn't know about quasars, we still would have developed VLBI. And I'm sure that since the Canadians were in on Maser observations, that they could have gone along in the race just as easily and just as effectively. Well, I'm going to just spend a couple of words in a transition to look at the future. But I'm not going to look at the future directly. I'm just going to say, where are we now? And with a little bit of marvel as to how things still can move fast and how you can end up with results that are not what you expected. The first slide is a time-lapse photograph. Yeah, it's the next slide after that is a time-lapse photograph of the W49 maser. We'll need a dark room. These are the maser spots in W49 done by Mark Reed, Jim Moran, and many others, observing both the Doppler shifts and the proper motions of the maser spots in W49. And as I think mostly everybody here knows, studies like this of the masers in the water vapor masers in Sagittarius B2 led to a 7 kiloparsec distance from the center, which is certainly below the canonical value, but probably at least as accurate and probably more accurate than any distance measurement heretofore. These W49 results, when fully analyzed, will probably give something approaching a 1% value for the size of the galaxy, subject to some dynamical considerations that may raise that uncertainty to maybe 5%. The same method can, in the future, probably be extended to get extragalactic distance scales. So the unlikely thing of finding the ordered electromagnetic phenomena like masers in space leads one then to having the ability to actually provide direct geometrical measurements of the cosmic distance scale. Now, in order to do that, we can have the lights on now. Obviously, color is velocity in the line of sight, and the velocity transverse to the line of sight is the length of the line in those articles, in those diagrams. One would like longer baselines. And those longer baselines have been talked about for some time. And 20 years from now, we can talk about who did what first. But interestingly enough, to go to longer baselines than you can get on the Earth by going to radio telescopes in space, OVLBI, orbiting VLBI. In 1971, Ken Kellerman, Joseph Shklovsky, Nikolai Kardashev and I held discussions in Burke about the feasibility of baselines extending to spacecraft, extending the length of the baseline to much beyond the Earth diameter. And you'll notice in 1971 is only 4 years after the first experiments in VLBI had been completed. So again, the time scale is very fast, but it's much harder to realize things in space. Here are proposals, proposals, papers, proposals, proposals, a workshop in 1984 that might lead to something, namely the Quasar project, and many of us are cheering on Canada in that effort because Canada at the moment is an active participant in the Phase A study being carried out by the European Space Agency to examine the engineering details of such an orbiting observatory. Now, of course, things are always helped if you have results. And so I'm going to finish with a result that is now approximately 1 year old, and this is an anniversary kind of thing, and many people have been reminding us about anniversaries. And so this is the first anniversary of the first successful VLB experiment done with an orbiting radio telescope. And in order to show the international nature, I choose this particular issue of the Nobuyama Post. You can, whoops, wait a minute. The TDRSS satellite is ordinarily, one antenna is pointed at White Sands, one antenna is pointed at a spacecraft, and it telemeters data from the spacecraft down to Earth. In this case, one points one antenna up at a radio source, but treats it like a spacecraft and telemeters the data from the quasar down to Earth. Because of the geometry, this TDRSS satellite is in a geosynchronous orbit hanging over the Atlantic Ocean. The only radio telescopes in the world suitable for long baseline work were the 64-meter NASA telescope at Tidbinbilla and the 64-meter telescope at Usada, while the Japanese also have the 40-meter at Nobuyama, but it turned out that the ISAS antenna is 64 meters in diameter, and when you can, you go with a big one. And the general burden of these remarks can be translated with reasonable accuracy. Space VLBI, TDRS, the TDRS satellite, orbiting VLBI, 1987. Whoops, what's that 1987 there for? Because this is a 1986 edition. And the pictographs here say that it works pretty well. As you go from longer and longer baselines, there's very large array, 2 R's in very, to very long baseline interferometry, space VLBI, and on out. So, with this indication that there's still a future, and also with a very cheerful remark that I hope that the Canadians will indeed take up the cause of this new phase of VLBI with great enthusiasm. Mesdames et messieurs, je vous remercie.
We're running a little late in time, but I think we have time for 1 or 2 comments.
What is the benefit of a laser OH laser line?
The order of a few hundred hertz to a few kilohertz. Makes it easy.
Do you use a Mark I type recorder?
We used a Mark I type recorder at Green Bank, and we used an ordinary recorder associated with the CBC 3300 computer at the other end.
I take it that was a popular Japanese magazine you had an excerpt from.
Oh no, that's due to a well-known Japanese cartoonist named Hirabayashi,
Or it was in
who is one of the workers at the Nobuyama Radio Observatory.
was it in a newspaper? Or
No.
He just did it locally.
Yeah, he's one of Morimoto's boys, and I don't know if you know Morimoto, but Hirabayashi is a chip off the old block.
But nice to see the Japanese cartoonists getting into the space game. I grew up in Japan, so.
Oh, I see. So you can read it.
Well, with the help of the dictionary, I'm all right on the speaking, but not so good on the, I'm a little worried about that 1987. I think that must be a reference to future planning.
I think it probably was.
Yes,
yeah.
because it definitely
Well,
was.
we did a second experiment in 1987, and it may be a reference to that.
Yes,
A new experiment is planned in 1987,
Yeah.
maybe.
yes, it definitely was a 1986
Sure.
issue.
Yeah.
Thank you very
Okay,
much.
Jack?